like in substitution reactions, it is possible to have leaving groups other than a halogen in the elimination reactions, but that's a really common place to start. So let's start with dehydrohalogenation, which is where a leaving group such as iodine, and then a hydrogen, actually a proton, at a beta carbon, in other words, a carbon right next door to the carbon that the leaving group is bonded to, one of those protons is also removed. So you can see in this case that there are two different types of protons. There's one on the beta carbon 1, which is actually in the ring, and then beta carbon 2 is the methyl group. And so you get different isomers depending on which beta proton is removed. And so if beta 1 is removed, you get the major product. There's more of this formed. And if beta 2 is removed, you get the minor product. And there are 4 protons that are beta 1 and only 3 that are beta 2. So that's one reason that this is the major product. And the one on the right is the minor product. But it also forms a more stable alkene. So in general, more substituted alkenes are formed by elimination reactions because they're more stable. This is an example of regiochemistry, which is where one isomer is favored over another in a chemical reaction. Okay, so there are 2 mechanisms, kind of like we saw 2 mechanisms with substitution, and there's a lot of similarities and there's some subtle differences. Besides, and of course, what the product is that you get. So just looking at E2, like in SN2, this is a second order reaction, meaning both the, in this case, base and the substrate are in the rate determining step and also in the rate law, of course. The mechanism is therefore one step. Everything happens all at once, and that's that one step of the reaction. We'll look back at the identity of these various different species as we on Wednesday, in the next set of slides. So, the reaction here occurs in one step, and we have the hydroxide. And in this case, hydroxide is acting as a base, and we can tell because it's subtracting a proton from the starting material. Here, our substrate. And so here are the electrons. The electrons are being shown to form a bond with the proton. The electrons in the carbon-hydrogen bond then stay behind and form the double bond, and that forces out the electrons that are in the bond from carbon to bromine. And bromine takes those away. It leaves as bromide, and we're left with our new pi bond. So that's one mechanism by which elimination can occur. The second method, you might guess, is 2 steps. It's an E1 mechanism, kind of like SN1, and also similar to SN1, a carbocation is formed as the intermediate. It also has first order kinetics. It depends on, that first step is the same as an SN1 step. And so in the first step, that iodine leaves, in this example, giving you the carbocation intermediate. Instead of having a nucleophile come along in the second step, instead of that, the base removes a proton from the beta position, and you are left with your alkene in the end. One thing to notice that's different between the E2 and E1 is that the E2 mechanism has a strong base that's really initiating this reaction. In the E1 mechanism, the base is weaker, it's just water, and so it's kind of patient. It hangs out and it waits for the carbocation to form, and then it removes the proton.